let's just jump right into the main topic. And I want to reframe this idea of asynchronous programming and parallel computing a little bit. The reason is, traditionally, what people have thought about parallel programming has to do with other threads, other processes, things like that. And that's not exactly the way that what we're going to talk about works. So we need to maybe, like I said, reframe it a little bit. So let me throw a little definition up here. So this is from Wikipedia. It says, asynchrony in computer programming refers to the occurrence of independent events of the main program flow and ways to deal with such events. These may be outside events such as arrival signals or actions instigated by the program that take place concurrently with program execution without the program blocking or waiting for the results. That's Wikipedia. Nothing here says, it means I created a thread. It means I created sub-processes, or I'm using multi-processes or thread pools or execution pools or anything like that. All right, so when we think of async and await and we think of asynchronous programming, we have to think more broadly about concurrent programming. Now, why do we even care about async and await and concurrent programming at all? Well, there's two core focuses that you might care about. One is, I want to take what I do and make it go faster. Either that's because I'm waiting on something a lot and I can wait on more things, or because I need to computationally just do more work in some kind of parallel algorithm. So we're going to focus on that first, the second one first. I need to take better advantage of some sort of computation. So here's a cool graph that charts what is often referred to as Moore's law. Now, there's a bunch of different graphs here. The maroon one that's still going up, that's technically what Moore's law is. The number of transistors in a chip doubles every 18 months or something like this. However, if we look at what people have often sort of thought of as the same of Moore's law is performance, either the blue line or the green line, that's no longer following that trend, right? Notice the CPU speed, the frequency in megahertz, or the single-threaded performance, they go up and up and up around till 2010, 2012, and then they don't just flatten off, they even go down a little bit. And the reason is we're no longer able to add more and more and more clock speed, but we're creating more and more cores. Notice the black line at the bottom, right? So our CPUs are much better than they were in 2010. I would definitely not want to go back to that. However, it's no longer the case that we can just ride that maroon line upwards, right? It's not like, well, my program's not quite fast enough, but if I wait, 18 months, it'll go twice as fast and everything will be cool, right? That's not true anymore. So what do? Well, if I go and I write some simple Python code here, and I mean simple, like here's x equals 1, while true, add 1 to x. It's a super simple program, but what it is doing is absolutely pinning that process. It is doing the best it possibly can, right? I mean, there's no sleeping, there's no network latency. It is full-on computation there. However, if you look at the CPU usage of my machine here, so this is my MacBook Pro with a Core i9 with 6 hyper-threaded cores, so it looks like 12 cores to the operating system. You can see I'm doing a very poor job of taking advantage of the power of my computer, even though I'm absolutely working as hard as I can in Python, right? And this would be the same in C++, it'd be the same in .NET, whatever. And notice the overall CPU usage on the entire computer is 9.5%, right? I believe it's like 8.333% that this program is using, and the rest is, Windows. So not really doing a good job of taking advantage of this, right? So if we want to take advantage of this type of computation and take advantage of this processor, I have to use multiple threads somehow, right? So that's one half of the story. And we'll see that async and await is not super good at that, but it is good at the I need to do more stuff while I'm waiting. Although in the end, we're going to talk about a library that lets you mix stuff that takes advantage of this situation and uses async and await. It's really beautiful. Another thing I want to start with is typically asynchronous programming is more complicated. With async and await, it gets way more approachable. It looks much more like synchronous code that you would write, but it is more complicated nonetheless. And so you have to decide about whether it is worth that. Often you'll see it's absolutely worth making this trade-off, but sometimes it's not. So imagine this is our program's execution in some kind of like profiler or something. And these green parts here, this is where we have an opportunity for concurrency. Not everything can be done concurrently, asynchronously, right? Like you can't send the email that says, here's your receipt for the product before you wait on the web service to charge the credit card before you decide to sell them the thing, right? Some things are just serial. They have to go in order. So some parts of our program will be parallelizable and some won't. And if we say, well, this is 15% here and that's 5% there, if we had unlimited parallelism, right? I have 12 cores, but imagine I had 1,000,000 cores, right? If I had 1,000,000 cores, I could make this program go 20% faster, right? That's like some sort of insane edge case, right? You can only basically make the green go to 0 at the very, very best. And of course there's overhead and that's not realistic. So this program, maybe it's a good candidate if you really need that 20%, but it's a trade-off. I'll show you a bunch of examples where that's not the case. One of the cases where that's really often not the case is when you're trying to use asynchronous programming for some form of scalability. Right? I want to be able to do more stuff at once. And the reason is often when you're talking about things like servers, this big rack of machines in the back here, they're running programs that are usually waiting on other programs running on other racks of machines. Right? I want to talk to the database. Oh, the database is over there. I send 10 bytes over the network and it waits for 100 milliseconds, which is forever in computing, and it sends back the answer, right? So during that waiting time, we could go do something else. So probably the most logical place to think about this is in the web, like processing web requests is like super straightforward to think about there, but you'll see it happens on client side. It happens on all sorts of places. So let's just dig into this idea around asynchronous execution on the web by looking at how it would be without asynchrony. So I'm going to try to draw a picture for you here that tries to explain computation time and latency and where that comes from. So we have 3 requests coming in: request 1, request 2, and request 3. And the green bars, those are supposed to show like how long each request takes. And of course, in a serial world, they're going to be processed one after another after another. So the first request comes in, we process it, we're going to send out some kind of response, and it took yellow bar amount of time from the perspective of the user. Right? They made the request, they got the response back. Well, while we're working on one, request 2 came in, but the user, they don't really care about that. They don't know about that. They just see like a much longer wait time coming in. And this little tiny request 3 that should take, a super small amount of time, 10 milliseconds or whatever to return. In fact, we had to wait for those other 2. So it took like 6 times as long as it should have. Now, if you think about, well, why is that? What's actually happening in these big green boxes? And we zoom in, and by the way, zooming in turns them purple. So when you zoom in, and we look at like what's actually happening, there's a little bit of framework code. Let's say this is Sanic. Actually, let's not say it's Sanic. Let's say it's Flask, right? Something that's not asynchronous. The framework code is running, and then we're going to talk to the database. We're going to send that request off like, hey, what user is logged in? I know I have this cookie. Their ID is 7. Who are they? So you pull that back and you wait for that response. Then you run a little bit of code. Oh, does this user have access to this thing? Oh, yes, they do. Okay, then I'm going to hit the database again and ask it for whatever that thing is. Do a little bit more work, turn it to a JSON to a dictionary, send that dictionary back to a template. The framework renders it. Done. The problem is we're doing nothing but waiting on some other system, right? Probably not even the same machine, and yet we're blocking everything, right? So a lot of the magic of async and await is to take these times that are red here and make them productive waiting, right? So instead of just going, well, we just got to wait to do the next thing, the system will free up that thread to go do other work until the database gets back to us, and then we can carry on with the blue segments and so on. All right, so if we were able to apply async and await to this, which is kind of a big if in the Python web space, but there's definitely some good options now, then it would look more like this. First request comes in, we respond same as before, but the second one, well, it came in, but we were waiting on the database, so we were able to trigger all the stuff that happened. And then request 3, maybe took a little tiny bit longer, but we were able to run it as well. So like this is the ideal scalability situation. It doesn't mean we're doing anything faster, but it does mean from the user perspective, we're able to do more of it at the same time. All right. And that's, of course, because these parts are now green and they're productive waiting. We can process request 2 in that first one and request 3 in the second one, and it's all good. Okay, so before we get to actually writing code with async and await, which we're going to do for most of this webcast, I just want to highlight, sort of put a roadmap, like where are we in the Python async space? So there's a couple ways to break this down and think about it. And there's a pretty hard divider line. And that divider line divides the ability to do more at once or to do things computationally faster, right? That first graph with Task Manager showing all the CPU cores. So in the do things at once, more at once, this async IO and async and await is exactly the situation I just described on the web. It's perfect for that situation and others. So is threading, by the way, because you hear that Python threads often don't really run in parallel because of this thing called the GIL, which we'll talk about. However, when you're waiting, excuse me, when you're waiting on networks, or something like that, it will CPython will release the GIL, and then it could go do other things until it waits on the network and so on. So it actually works pretty well. It turns out the async IO programming model is much simpler to reason about on a whole many ranges of ways. So it's good, but they're kind of in the same category. And that's not true for other languages, right? Like Java and .NET, the threads would span, both sides here. On the do things faster, because of the GIL, we can break this into multiple processes and work on it here. And it's faster in some sense, but it has a lot of overhead because you're spinning up a bunch of processes and doing IPC and all that kind of stuff. We could also use C or Python, and that's a pretty interesting option. Like Python actually, so if you're not familiar with Python, it's like Python, but it gets compiled to C code, which then gets compiled to machine instructions. And one of the features of it is it has kind of like a with block, but you can say no GIL, no global interpreter lock. And then stuff that happens inside there is entirely Fred 3 to go do whatever it wants. So that's pretty cool. There's a lot of restrictions about what kinds of things you could do in those blocks, but it's certainly a way to go do things faster, not just because it runs faster, but because it has this parallelism capability. All right, then we'll talk about at least one of these other libraries. Trio is a pretty cool library that lets you coordinate stuff more on the left than on the right. And Unsync is really cool. Unsync lets us bridge all of these worlds in like a unified API. So it lets you take async code, threaded code, multiprocessing code, and treat them more or less all like Async IO, which is great. Okay, final thought. I mentioned the GIL a couple of times. Almost everyone's heard the GIL. They hear it as a bad thing. It's often a challenge, but it's usually not nearly as big of a challenge as people think. It's mostly a problem around the computational stuff. And on the computational side, most people use things like NumPy and pandas and so on, which are not subject to the GIL, sort of for the same reason I talked about with Python. So anyway, the GIL is actually a thing that has to do with Python memory management. And the restriction is that Python can execute only one interpreter instruction at a time, which means it doesn't matter how many threads you have, you can only run one of them at a time if they're running Python code. Okay, so if you want to dig in more to that and understand it really well, then realpython.com has a great article over at python-gil on their site. So you can check that out. All right. Remember the Mindshift thing I was telling you about? So let's talk about that real quick, and then we'll write some code. So typically when people think about concurrent programming, they think, oh, I'm going to have this main thread that runs along. Then we're going to kick off some other background work, and it's going to run. And then we're going to kind of wait. We're going to wait until we get to this part right here, right? We're going to do some work. They're all going to run, and we're going to wait until they're all done, and then we'll carry on and finish, right? However, if you think of IO-driven concurrency, it doesn't work that way. And this async and await stuff is largely what we're talking about. So we have just one thread. It's just running along, doing its thing. It's probably the main thread, but it doesn't have to be, as you'll see near the end. And what we're doing, remember those blocks I was talking about, like framework code, database code, and so on. Those little segments of each function or each operation can be broken into small slices. Like maybe here's one things that have to happen during one request separated by waiting on external systems. Like here's another. If we take our work and slice it into small enough bits, and while other parts would be waiting, we can run these tasks. Say like, well, task 1 would have been waiting. We can run task 2's green little bit. It will feel and seem like basically they're running in parallel. Okay, so this is the underlying idea for Async IO, is that we're going to take our functions and break them into little bits, basically demarcated by where you say the word await at each step along the way. Okay, so this thing that does this work here is going to be called the async event loop, and it plays a central role. All right, so let's go and look at something that does not immediately feel like it is about multi-threading, but turns out to be. So I'm going to open here we got our repo of all of our stuff. I'm going to throw that on here, fire up some PyCharm. Now there's a bunch of different little examples in here, and the blue ones, each blue box is a source root or the top level of some program. So
hey,
we're
Michael,
going to start with this.
Switch over to do some coding.
Yeah. Let's take some questions. Right, it's a good place.
A lot of good questions.
All right.
We've answered a good number of them, so I'll save the ones that require talent for you. Is Async IO performance similar on Windows, Mac, and Linux?
That is a good question. I have not profiled it, but I don't think it's super different. What you will see is there's the ability to actually replace the Async IO event loop with something called UV loop. And UV loop is pretty significant in terms of how much faster it can be. And that I don't believe works on Windows, right? But here's the thing. Like, it depends. What does it depend upon? It depends on whether you're doing fine-grained or coarse-grained parallelism. If you're saying, I want to take calls over to other web APIs like microservices or something and fan those out with Async IO, that'll blaze on any of the systems. It doesn't matter, because the size of those waiting blocks, like the amount of work you're doing, is like hundreds of milliseconds. If what instead you're doing is like, I want to take something and break it into very fine-grained computation, and I'm doing 1 million awaits or 100,000 awaits a second, then all of a sudden the computation, the latency or the effort of that really starts to tax the async event loop. Then UV loop would be like 4 times faster. So if it's coarse-grained, it doesn't matter, because most of the work is actually happening in the chunks. But if you have lots of little tiny chunks from my diagram there, then it would matter.
And these things touch on some pretty low-level operating system things too. So
yeah,
it's way outside of the control of the Python runtime.
Yeah.
Okay, so we got a bunch of questions. We'll try and speed up on some of the answers. This one just came in. How would you rate Async IO compared to threading when it comes to learning curve?
I would say 1/3 effort. So 3 times better.
And then I would also say Async IO is harder than you think it is. So
yeah,
even though it's easier than threading, it's still.
I totally agree.
Take the course.
That's right. Here's the thing though, like return values become simpler. Where do I try and catch, or where might I try accept blocks go, and how does that handle? Like on threads, all that happens on the other thread, and you've got to pull the errors back over. With Async IO, the threads are marshaled back to or the errors are marshaled back to where you are. Maybe they never left because the event loop, the way I talked about. But so those types of things get simpler, and that's why I said 1/3. But yeah, there's fewer chances for deadlocks because you don't use locking in the same way, because again, there's no threads. But still, it's still parallel programming.
For this next one, before going on to the next questions, someone asked, could you put the URL back up for getting to your material?
It is in the chat, and you all should see it there.
Oh, okay, good. Good.
But I'll put.
All right. Yep. Everyone, take a look in your chat window. So there too. Any recommendations for a book on Python async?
I don't have great recommendations. I can tell you that there's some really interesting coroutine coverage in Fluent Python from Luciano Romalo. And
that's what I was going to recommend, but it's not modern, so to speak.
Yeah, exactly. I don't think it has async and await. I think it's like 3.4, not 3.5 in terms. Like it has async IO in the prior API for that, but it's
And
a
even
good fit.
Python 3.7 has some syntactic sugar to make things a little easier than 3.6. So
Yeah,
if your
yeah,
book is 3.6, it's a little out of date.
yeah. It's surprisingly many changes for async IO in 3.7.
Next point, if you could emphasize that we sometimes use the word async when we're describing a technique, but there's also a keyword in Python called async, which speaks to a specific implementation.
Yes, absolutely. We'll get to that in just a second.
All right, cool. So there was a question, I think I got the answer, but I'll let you speak to it a little bit. If you use async, should you avoid the multiprocessing module?
No, they serve different purposes, and that has to remember the roadmap.
Yep.
Where you are in the space, right? Like if you need to do computational stuff, if you're looking at that task manager window and you're like, well, that's 8%, that's not super. How do I do more of that, right? That situation is where you would want to go towards multiprocessing, or even something like Python.
And in fact,
So
there is an Async IO wrapper around multiprocessing called AIO multiprocessing.
yeah, nice. And yeah, I'll show you the unsync thing as well touches on that.
Oh, good. And last one in this batch, and while I was talking, two more came in. Are there any ORMs, object relational mappers, that have native support for Async IO?
Yes, there's some for Postgres, there's some for MongoDB, and I'm sure there are some for others. I'll show you at the end, actually.
All right, good. All right, proceed. Thank you.
All right. So pretty much from here on out, it's going to be mostly code, which I think is the way to do it, right? It's a way to understand this. Now, I want to start with something that doesn't feel like it has anything to do with async and await or parallelism or anything like that, but understanding how it works has like super close parallels to the way async and await methods work. So let's just look real quickly at a standard numerical sequence. Okay, so we're going to create the Fibonacci numbers, friend of all demos. So we're going to create the Fibonacci sequence here, and we're going to do it in the, like CS 101. I'm just learning programming, straightforward way, right? So the Fibonacci numbers, if you're not familiar, are the numbers of, if I can find my keyboard, we add those two numbers to get the next, and then you take the next two numbers and you add them and you get the next, right? And so on. So those numbers, we want to generate that sequence. And as you can imagine, adding two numbers to get the next sounds like an infinite series. So this one is going to go through and say, I'm going to create a list. I'm going to go through and I'm going to compute the next ones. And isn't Python beautiful the way you can do that in one line right there? And I'm going to add it to this list. And then when I've gotten all that you've asked for, I'm going to return that list. Well, that's great when you know I want 50 Fibonacci numbers and you run it. Let's see if I'm running the right one. There we are. There's a bunch of Fibonacci numbers, okay? And I'm actually only showing some of them. We'll see why that's relevant later. But what if I'm trying to explore, right? Am I trying to figure out, well, what's the Fibonacci number where the property is the first one is prime and the second one is like that prime squared plus one number or something silly, right? I'm looking for something and I don't know how many I want. How do I do that? Well, that becomes a big problem, right? So we can restructure this. So we don't have this. Oops. I want to comment that out. And let's use a generator, right? So I can change this. Come down here and I'm going to say, well, we don't need this. And we're going to come over here and just say, well, what is that, an infinite sequence? That's cool. Let's do that. So we'll just, while true. And instead of adding them to a list, we're going to just go to Python and say, here's one of the items in this sequence. Here's the next, right? Here's one of them. Go do it again. Here's one of them. And now if we run this, you're going to see some interesting things. First of all, I'll put a breakpoint here and here. And we hit it in the debugger. Run along. No, it hits here. No, the previous program, the very next thing I did, if I hit a step into my code, is it would go here and run it, and then we would get all the numbers. Well, that's impossible with an infinite series, right? So we're going to step over, and what we get back is a generator. As we pull on the generator, we can kind of break this work into little bits, demarcated by yield, okay? So we could step in. Notice you can see current 0, next is 1. I'm going to increment that, return 1, and then we're going to go print 1 out, and now we're back in our code. And then we pull a little more, and we jump back in, restarting this function here on line 17 with those numbers. Let me bust through a few loops so it's really more obvious. So now I'm back in, and we jumped in here, and it's 2 and 3, right? So this back and forth, this ability to run part of the function, give some answer back, run another part of the function, give another answer back. This is very much how the same system would work if we put the await keyword here, right? It breaks the work up to say, well, we're going to run up until this point, and then we're going to let go of the execution, but then you can pick it back up where it left off. The trick is to pick it back up where it left off when the other thing is ready, right? And that's Python's async story there, all right? So if we go ahead and just let this run to the end, you can see exact same output, right? But we didn't put it all in the list and compute it all at once. We broke it into these subsets of execution, kind of like the big event loop graph with the pink and the green and the blue and so on. Okay, so that's one of the core ideas I wanted to touch on for you. Now, let's first look at something that is a little bit contrived, a little bit fake, but then we're going to move on to actual things doing actual work as a follow-on. But I want to keep it as simple as possible. So here's a program. I'm calling it sync program. I'm going to just run it real quick. Let me show you something before. So we're going to have 2 parts of this program. One part is going to generate some work to be processed. This generate data is going to throw it into some kind of data structure. Here on line 10, it's a list, but it doesn't really matter. It's going to throw it in there, and then eventually, after it's all generated, this process data is going to take the work that was put there and like execute it, do the work with it. So imagine like a async message bus type of thing. Work's coming into the queue, work's being picked up as it comes in, something to that effect. Okay, so we're going to run it, and you can imagine we're going to run along here and wait. That's going to run, and then that's going to run, and then that's going to run. Right? That's just the way it goes because that's how programs work. Oh, we're also using Colorama, which is a cool library because it turns out, sure, let's update on YZSH. It turns out when you're trying to understand this concurrent programming stuff that it's really helpful to have color. This part of the program is blue, that thread is green, things like that. So that's what we need Colorama for. So here we let this run. You can see it should be no surprise that we're generating item 1, generating that first batch of 10, and then it's going to reset, and we're going to do it again. And then at the end, we're going to process it. Now, at the end, it's going to put out not just what it processed, but how long has that thing been waiting to be processed. So the first one, it took 20 seconds to generate that data. So it was 20, almost 21 seconds to actually get to it. So you can think of that as like latency. The item went in, 20 seconds later, it was processed. The best we did at the end was 10 seconds to process it. Now, there's a little bit of, the part I would say is fake about this is I'm using time.sleep to say, imagine this takes a while to do this work, right? We're going to get rid of this concept of sleeping in, like wait on real systems in a bit. But this simulates somehow waiting on another system, a database call, a microservice, an external API like Stripe or whatever, okay? So this first round, let's do like a suspension of disbelief and imagine that is a useful external service, and then we will actually talk to useful external services. Okay, so my goal is to take this program and convert it to an async and await version. So over here, I have the same program marked up just so we can fly through it real quick about what we need to do to take this program and convert it over. Okay, so the first thing that we need to do is we need to create this async event loop. All right, so remember here, the thing that manages those little slices and execute this one and that one and so on, we need to create that. So the way we do that is we go over here and we say loop equals async IO and import that and say get event loop. Okay, so we're going to work with this. And if you really want to get some nice help from PyCharm, you could say this is an abstract event loop, I believe. Oh yeah. So now if you say loop dot, you get all the goodness. Okay. Now, what we're going to do is we want to convert these functions so they can be executed with async IO. And this gets to that keyword we were speaking about in the question section. So let's go ahead and convert this function to async IO. So there's 2 steps. The functions have to be explicitly marked as async, right? This is not technically necessary the way the language works. It could determine, oh, you're doing stuff with a wait in here, so boom, it's async. But as a good like understanding of this program that it is special, the async keyword here is really nice. And then what we want to use here is that we're going to use a different type of data structure. So I guess I could change that up here. Yeah? And we'll drop the to-do bits as we do them. So this is going to be an async IO, a queue, like that. Now it turns out that that is a nicer thing because it allows us to, like we did with the yield keyword, break up the work around it. Like I'm going to put something into it or wait until it has something. And the thing that's cool that like a list doesn't have is I can wait until it will have something. Like it doesn't now, but so I'm just going to put my method to sleep until something appears, and then boom, I'm awake. Now PyCharm is saying, oh look, you said you give us a list here, and now we're not getting a list. So let's fix that real quick. Say those are not lists, those are queues. Yeah, that's good. Now notice this does not take and append like it did before. Let me make this a little more obvious here. This is going to be, that's not the right word. This is going to be work or something like that. So the thing we're putting into the list is a tuple, which has the actual thing to work on and the time it was added, so we can compute that latency, right? So instead of doing this, we're going to come in here and we'll say data dot put, and I'll put some work in here. Now notice there's something wrong here. And it's like, well, what is happening? The problem is that this thing, we need to actually await it because put itself is an async method. Anytime you call an async method, well, most of the time you call an async method, what you want to do is you want to say, I'm going to run my program down to here, and then this thing might have to wait until it can perform its operation. So I'm going to let other stuff happen while I'm waiting for that to do its work. And then when it's ready, I want to resume and run here, okay? So the other thing that we want to do is time.sleep is not super helpful. Whoops. It's not super helpful. What we need to do is a different type of sleep. I got to know to not switch between Mac and Windows and the hotkeys. Okay, so we don't want to do this. We want to do something that is awaitable, because if we look at this definition, it's a def sleep, not async def sleep. So any chance you get to call an async function is better, and async IO comes with a sleep that is itself async. Now, PyCharm should also be upset with this. Here, actually, oh no, I went too far down. Here, let's do it here. That's why it's not upset yet, async. So now it's saying, look, you need to await this because you're also calling an async method. So remember how we broke up our Fibonacci sequence? We'd run to here, and then we let other stuff happen on the event loop. And then we run to here, and we let other stuff happen on the event loop, even while we're waiting. And most of what we're doing is waiting. So let's do the same here. The reason that PyCharm didn't freak out down here is because this is not an async method yet, but I can see the bottom it does. Okay, so we got to await this. And this, we're not going to use this pop, and we don't have to do this little fake wait thing. All of this can just be reduced to this data dot get, like so. Now what's cool is if I say, let me try this. If I go item equals that, now this is going to crash. Well, let me just say that the type here would be, so item is not a value. It's not that thing that we put into the queue. It's not that tuple. It's actually a coroutine. So if we don't await it, we get just the coroutine. But if we say await, then what happens? This is a tuple. So putting the await here like basically waits for the coroutine to finish and then converts, grabs out its return value here. Okay, so this is all looking pretty good. Yeah, so our two functions are good, but now when we call them, some stuff is not going to be great. I guess I could go and try to run it and see what happens. Let's run. Yeah, it didn't get super happy about that. It said generate data was never awaited. That's a problem. So what we want to do is there's a short version and a longer version. I'll go ahead and use the short version. So we can do what's called gather with these with async io.gather, and that will convert all of these. Once the appropriate commas are in place, we'll convert them to a single thing that we can then wait for them to be completed. Actually, say it like this. And then down here, I want to go, I'll say async, loop.run until complete task, like that. Make sense? So this like starts the work. It doesn't block on it, right? Kind of like when we call the fib, like this will immediately return and then run to here. And it's not until we call run until completed that it will stop. Okay, let's try again. So now if we run it, look at them running in parallel. So the first two generated their stuff right away, and the other stuff is grabbing it. Most notably, though, look at the latency thing there, right? The worst latency we saw was like 1 second, not 20. And it also happened to run 3 times faster. However, one of the nice things here is what if we did this? Again with those hotkeys. If we had, let's say, 4 of these, and they only each expected to do 5 amounts of work, right? We could add more parallelism to the system. And now if you look at the latency, it's 0, right? Because anytime work comes in, we can just grab it and work on it because there's more things waiting to receive that than actually is generated. So not a whole lot more work. It turns out this API is a little clumsy, right? Like the necessity to create this event loop is kind of a little bit too much. And to start them like this and this gather and then run, it would be nicer if there was a cleaner API, and I'll show you that cleaner API at the end, but this is a pretty good start. Paul, maybe this is a good time to take a couple of questions.
A couple. What's the upper limit on couple? Got a lot of good questions. Just
3 minutes. As many as you can fit in 3 minutes.
Limit, say we'll save the rest.
Yeah. We'll sit around. I'll stay and do questions at the end for sure. But I want to make sure there's a few more things I want to touch on before we.
Yeah, indeed. And I got to admit, this example that you have with the colorama and the building it up and seeing the change in elapsed time is fantastic. Well done on that.
Thanks.
Django. Know of any work with the Django ORM and Async IO? I don't.
As far as I know, I don't think it supports it.
Yep.
Yeah, I don't think so.
Have you ever looked at the async and await keywords in JavaScript?
No, I've looked at them in C#. I'm excited to see them coming there, but I think Python had it before then, and .NET. I think this idea, async and await, actually came from C# originally. Yeah, I don't know very much, but I'm excited to see it there.
Yeah, Python got it around the same time that the world of JavaScript was doing these experimental things that would transpile to ES5. I've done some with it. It's a layer over promises, and the developer experience is very similar to the developer experience in Python. I can't say that the implementation underneath is similar.
Yeah, I know nothing about the internals, but I'm guessing like the then and catch and all that is converted to these await blocks and stuff.
Right. So someone asked, is this what in olden days would be called cooperative multitasking, where the developer decides when to give up control?
Yes, as opposed to preemptive multitasking, it is.
Yep. I'll save this one until the end about Curio and some of the other things. Do you want to stop and continue or go through more?
Let's go do one more and then we'll come back.
Right.
Okay. So this could use a good graphic. So just quick review. Here's the anatomy of an async method. We have this async definition, and then we await any asynchronous methods that we subsequently call within them. You'll see not always right away, but generally this is how you want to do it. And so here get is an async method, so we're going to await it to get the return value. Otherwise, what you get back is not the data you thought you were going to get. You will get a coroutine. All right, so we saw with our synchronous version, timing wasn't great, latency was bad. We saw with the async version, the latency is way better, the time is faster, and we can throw more and more concurrency at it to solve some of the latency problems as well. All right, so the way we had it structured before, we're getting about 60 times less latency. We talked about UV loop. UV loop is a faster implementation. They say ultra fast, but 4x. What does that mean to you in terms of ultra? Anyway, it's very nice. It's super easy to use UV loop, long as you can get UV loop to install on your system. It may work on Windows now. Last time I tried, it didn't, but you know, who knows? So you basically run this one line of code at the top: async IO.set event loop policy to UV loops event loop policy, and everything that uses async IO is now switched to UV loop. That's a pretty cool bit of async IO's implementation. So this is a nicer thing based on libuv, and it's like all written in C and stuff like that. All right, but like I said, that looked fake, right? Like, okay, well, Michael, you say time.sleep and you switched it to async IO sleep and it got faster. Whoop-de-doo, right? How about actually showing me something happening? Like, let's let some sparks fly, right? Okay, sparks you want, sparks you get. So let's go and put this away. Put these away. Now let's go, not look at that. That's exciting, but not it. I want to look at this other thing. I want to look at talking to a website here, okay? So what we're going to do is, of course, we're going to use Colorama because Colorama is great. And we're going to go to some random website called talkpython.fm. And if you put the episode number as just the URL, it will find its way over to that episode. And what we're going to do is we're going to use requests to suck down the HTML, all of it, right? And then we're going to pass that off to get title. Get title is going to use the beautiful, beautiful soup, suck out the title, and then print it out for us. Okay. And then there's this part that kind of derives that for a bunch of different ones. So range 150. That's a little out of date. Let's go with 85 to 200. How's that? So if I run this, it's going to go for episodes 185 to 200 to my podcast, pull down the data, and process it. Now, the site is super fast. It has like 10 worker processes spread out behind Nginx. It could totally handle this in parallel, but this thing is going one at a time. Get this, process it. Get this, process it, right? So let's see how that goes. Maybe I need to pip install requests. So each one of these has a requirements, as you'll see. I'll remember to do it for the next one. So if I run this one, oh my gosh, did I say I was going to remember to do it? I'll just do it like this. There we go. Now it should work. So if we run it, you can see it's getting episode 185 and it got it. And then 186 and it got it. 187 and it got it. But what are we actually doing in our program? We are waiting like 99. I don't think it's 99. Let's see let's make this explicit. Watch this. Let's profile this program. Let's put some numbers behind this. How much of the time are we waiting? Is a lot. We have to wait to even find out how much we're waiting. All right, here we go. So let's go over here with the call graph. Zoom that bad boy in. Okay, so it looks like some stuff is happening around network sending. It looks like we called main once. We called get title range, and it called get HTML 15 times, and that's 95.3% of the time, 10.8 seconds. So over 95% of the time we're waiting. That means our program should be able to go about 20 times faster if we could somehow not wait. Well, oddly, the keyword await is allowing us to not wait. So let's change this. I'm going to take exactly this. No, I guess I'll leave it like this. So what we're going to do is we're going to go over here, and just like before, we're going to run this other one. In the beginning, it's the same, but we're going to convert it. So let's go and say, hold on. Let's go over here and create our event loop. We'll say like before equals async IO get event loop, like so. And then we want to say just this, loop dot run until complete, that. Okay, so we're going to need to make that function async. You can see that it's not super happy that we're trying to run an async thing and passing in a non-async output. So let's start here. Now, this is going to be a little surprising because it feels like it should totally work, but it's not going to be the most amazing thing you'll see. Actually, it's super instructive in that sense. So we're going to say that's async. And what we need to do is the get HTML needs to be async as well. The get title, we already have this string in memory, and we're just jamming on that, right? This right here is probably the 5 other percent, right? The 5% that we're not waiting is doing that. Okay, so there's no way or reason to make that async. Maybe multiprocessing, I don't know, but we're not gonna not worry about that aspect of it. We're going for the low-hanging fruit of get the 95% to go to 0. All right, so then that means over here, this get has to be async, and that means we need to do this, right? But hold on, request is not async enabled. It's not, I can't do this. So let me introduce you to another bit of magic called AIO HTTP. So AIO HTTP is a cool library that will let us basically do request-like things, but it's natively built to support, as you can imagine from the name, Async IO. I'm also going to install this in a sec. But so let's copy that path and pip install -r that thing. So we got to install those. And it's going to take just a moment. And I'm also going to pip install AIO DNS. I don't believe that works on Windows. It's not really necessary, but it makes things a tiny bit faster. So we'll go with that as well. Here we go. So now we can't do this. We can't just make that asyncable. So what I'm going to do is I'm going to write some more interesting code. I'm going to come over here and put into a with block. I'll say with AIO HTTP client session as session, and I'll say with session dot. Let me do this. So what you got to do, I was trying to avoid, is you have to make like this operation of getting the session is asynchronous. So how do I make this work? I have to say async with, and that's a little bit of funky syntax, but you can do it. Then I could say async with session dot get, right? Then I just give it the URL. And then I'll do something that's like a little bit less satisfying. I'll say, as response. And so I want to do that same code, response.raise for status. Oh, cool. Yeah, that didn't come up before, but now it does. And then this is a function, if you go to the definition on it, and it's an asynchronous function. So there's 3 async steps here. Getting the session, there's an async begin the HTTP request. A response comes back, but maybe we haven't streamed it back from the server. And so this is reading it back from the server, and that also has to be awaited to go from a coroutine. What am I missing here? Async def. Well, let's see. It should work. Yeah, I think it's just readable. Let's try. So let's go ahead and try this and see if it works. It's not going to work as amazing as you thought, or it's going to crash. No, I don't know. There's just some weird detection that was working right. So much better, right? Here, check this out. Here's the old one. Here's the new one. Okay, that's fine. Looks the same, right? So what gives? Why is this not any better at all? Well, the reason it's not any better is what we're doing here is we're saying, I'm going to go down here and I'm going to start one operation and I'm going to wait for it to finish. And then I'm going to start the next operation. I'm going to wait for it to finish. Like if there were other threads trying to do this, maybe it would help, but there's not, right? It's just, we're not actually doing more. So what I need to do is start all the work and then process it. So in order to do that, we're going to do something a little bit different. I'll say tasks equals this list. And then I'm going to do the same thing, but instead of waiting on it, I'm not going to await. I'm going to say this, tasks.append. Now, it would be cool to say that and then go do some more work, but this is one of the slightly annoying limitations of Python's async implementation. This will go away if we talk about unsync. But anyway, this is not enough to get it going. I need to like kick it off. And the way to kick it off is I go to my loop, which let's do this. let's pass our loop in here and say this takes a loop, which is an abstract event loop, like so. So I can go over here and I can say loop.create task, like this. And that will kick it off. It won't wait for it, but it will begin it doing its work. Then I can just come down here like this. I can say for t in tasks, I would say, so I want the HTML back. So I'll say HTML equals, and you can't exactly say t. So what you're going to do is you're going to say await t. Now we also see, notice here, we also have n we need, because before it was just part of the loop, but now we don't know which one. I mean, I guess I could do a little math, but that seems sketchy. So what I'm going to put in here is the number as a tuple, and then I can unpack it when I get here. So say task n equals t. Let's just do it like this. Task n, and we'll wait task. How's that? Okay, so we can start all of these, and then we can wait on them, and then work. And that will kick them all off, maxing out the parallelism, and then we're going to process it. So let's do this again. Look at that. They're all running. Boom, they're all done. How awesome is that? Sparks. So it's totally working. I'll run it a few more times for you. Go, they're all running. Bam, process them all at once. Really, really nice. So that way we're able to use Async IO. And if we were to profile that, if we had enough parallelism, I guess, we could probably get it something like 20 times faster, because 95% of the time we were waiting, and you can tell there's not much more waiting. We start all the work, and then all the work is processed. All right, Paul, that's probably a good point for questions.
All right, let me hit one. Okay, let's see. Is async something that can be effectively used in conjunction with something like tk-enter to manage GUI response to background processes? I answered that tk-enter has its own main loop, but a bunch of these GUI frameworks also have integrations with other loops.
Yeah, I don't really know anything about tk-enter in that regard. I have seen something like this for Qt, which is another GUI framework, but I don't know. I think there's probably some kind of bridging layer you could put together.
Right. What do we do when we have built-in functions that don't have async and IO options? My answer was go look for community re-implementations as async, usually with AIO as the prefix. You want to comment on this?
Yeah, that's often the case. Like the Postgres database access layer doesn't have any built-in ones, but there's an extra one there's a separate one that does have AIO in the name somewhere that does. And so you would switch to that one. If you don't have that as an option, stay tuned for the next little demo in just a second. Which we'll just take a moment. I know we're almost out of time, but it will also just take a moment.
It's fine. You can go a little later because that is an important one. I believe the answer to this is no. As far as I know, if I have methods in a class with async, then all methods in the class need to be async. That is not correct.
I don't see why that would be true.
Yep. Could you explain a little bit about coroutines? What is it? What is it used for? Be brief, because they can also look it up themselves.
Yeah, sure. So coroutines basically, like, this will create an async coroutine that can be run. There used to be a decorated way to say it before we had the async keyword, and that's like the Luciano Romano style API that we were talking about earlier. It's just like a generator function in the sense that it allows you to run a little bit and then get like an intermediate return value and then resume it again. But what we do is we like run it up until you see the first wait keyword runs synchronously up there, and then here it's like set free, so it kind of goes to sleep and other work happens on that event loop, and then once this is done it resumes that little bit. So they're basically functions that can sort of execution-wise, be broken up into these bits, and the demarcation point is where the await keyword is. And it's not super simple, like, well, this bit of code runs and then this bit of code, because there's a loop here, right? Like, it's a conceptual thing, not a syntax thing.
All right. This next one is a really good one. How to do exception handling with Async IO. I believe I gave the right answer, but we'll hear it from you.
So like that. So like here, let's make get title, throw an exception. Did I put that in the right place? I don't think I did. Oh, you know what? Hold on. Maybe I have it wrong, Paul. What do you got? What did you say?
That's one of the nice things about async is inside the code that's async, you can just act like you're doing synchronous programming.
That's what I thought as well.
Exception handlings.
But it doesn't look like I caught it.
Yep. Now I don't think I've got the answer for if that exception continues up outside to the work that awaited it.
Yeah. All right, I'm gonna have to play with that some more.
I believe you wrap your exception handler there as well, and it's all just fine. It's as if
that's
you were doing synchronous programming.
Yeah, exactly.
All right, next one. Feel free to say way too much for this one. How can I do multiple database requests with Async IO if I have SQL Alchemy, which is not Async IO compatible?
That's a good question. So I think also the unsync stuff would help. Basically, you can run those in threads is one of the answers. And when you go to the network layer, CPython will release the GIL, because that's what happens when you do network and file calls and things like that. So that's one option, which is not super great, but this unsync thing is a pretty cool unification of these APIs, which I think makes it more palatable. I wish SQL Alchemy had better async support. There's other things like Peewee ORM that do have native async support. I think it's an extension for it, but
okay,
you basically got to look outside.
That's definitely one, because the creator of SQL Alchemy is on the record saying that what you think you want isn't what you need.
Yeah, I know, and he said that on my podcast, but he said that 4 years ago without async and await and async IO. So maybe his opinion is changing. Yeah, maybe. But that was the last I've heard from Mike Bader as well.
Yeah. A bunch more questions came in. I don't know how willing you are to how much time you have afterwards to answer questions.
All right. This is definitely a topic that drives a lot of questions, and it's very interesting to have these conversations.
All right.
But let me show you one more thing, and then I have nothing left to show, and then we can just have questions. How's that?
Wonderful. Thank you.
Okay. So this stuff worked out really well, as you can see, because what we're doing natively supports Async IO. But we've already had some conversations like, well, what if some stuff I do has Async IO support and other doesn't? It's like, well, use threads. Now you have these two weird APIs that, like, how do you put them together? That's really hard. And multiprocessing, like, we haven't even talked about computational work, right? Like, one thing I could do that would be pretty trick is also to turn those into multiprocessing calls, so that we actually, because you saw, like, if you watch this run, notice those all go instantly, but those, even though you probably can't tell over the screen share, but there's a delay, a small delay between each of those. So we could get more parallelism if we computationally did that in beautiful soup on other processes, right? So, like, how do you mix these? Sometimes you want to mix them, right? So there's a cool library called Unsync. And I'm going to show you something real quick here, because we're low on time. So this is going to do some work that is computational. It is going to do some work that downloads something. It's going to do some other work that downloads something. And imagine in your mind, let's see, I'm not sure which one of these two goes which way. Yeah, imagine in your mind that, like, actually, let's look at this one. We're going to try to parallelize this and throw in async IO at it, okay? But it turns out to not be super helpful. So we're going to turn them all to async so we can treat them similarly as tasks, even though this computational one actually has no weights. There's no real point in where it breaks. Okay, and here, this one, imagine this download sum uses an API like we're calling a package, like down inside, it's using this code. This one is built to support async and await. So it can use, internally, it's using this. This other one, other API, maybe this is Stripe or Slack or some API like that, it's not built for that, right? So it can't use this. However, this thing I told you about the network, releasing the GIL when you talk to the network, this would be okay with threads, but it's not okay for async IO. So that's going to be bad. And then waiting, actually, this is totally good. So what I'm going to do is I'm going to run this program, and you'll see some of it's really fast. Computing, just single threaded. Downloading the first one was crappy, but the second two were better. And then waiting was really fast. Okay, so notice we're running this at 5 seconds. If I run the one that's just pure single threaded, it takes something like 9 seconds. Okay, and it's doing like real computational work. And the computational work is like about a second. So you can't really get it any faster than that. This one takes 10 seconds. So we did get a big boost from doing it this way, right? We did say, let's just treat these all like tasks, and sometimes we'll get some benefit and sometimes we won't, okay? But this compute sum, the way Python's GIL works, really needs to be in a separate process using multiprocessing. This one, let's say that's the async IO enabled one. That one is totally fine with async and await. Excuse me. But this one, it uses requests. We can't use async and await on it. But because of the network stuff, if we use threads, that would have been great. This one also totally fine using async and await. So this unsync library is really, really cool. So what we can do is, like, remember I told you I don't like this get event loop and then creating the task, and then you got to start the task on these, and then you got to run until complete. Couldn't there be a nicer way? Like, what if we just said, you know what, forget that. What I really wanted to write was this compute sum 3 times, and then this download sum. I want to do that 2 times, and same, right? Just call them like functions. And this wait sum, let's do that 4 times, like before. Like that. I just want to call that, and we find some way to wait on them, okay? So this unsync library is really cool. So let's do this. We'll say from unsync, which is not installed. Thank you, PyCharm. Import unsync. So what we can do is I can come down here and I can say this function is an unsync function. And unsync looks at the function and decides a couple of things. If it's asynchronous, it runs it on the async event loop. If it's not, it runs it on a thread. But I can tell it this is CPU bound, and now it runs it on multiprocessing. And it's the wrapper of the function that decides that. They all use the same API. Okay, so this download sum, this one's truly an async thing, so we can just say unsync. This one actually is not really doing an await, so we just say unsync like that. It knows it's not async, so it's going to run it on a thread, which is fine because that right there. And then this one is also unsync. So by doing that, we can treat them all the same as this thing called an unfuture, which is kind of funny. But what we can do is I can just come down here and say t dot result for t in tasks, and that'll block. That's it. So none of this event loop stuff, none of the creating a task to kick it off because it looks like I called it, but I didn't actually call it. And then they all have the same. And then it knows that goes on a multiprocessing, that goes on async IO, that goes on threads, and that goes on async IO. All right, let's try this. Bam, look at that. Is that trick or what? So when you have these things, you're like, this part of my library doesn't support that, right? You could run that on a thread other than like, well, all of a sudden that makes the API super complicated. Wrap it in unsync. And guess what? It's not uncomplicated anymore. It's like this beautiful unification of these 3 different APIs, and it just figures it out. Here, I'll run it one more time for you. Remember, it took 10 seconds, and then I was able to get it down to 5 with async IO. Notice all that stuff happening in parallel. Okay, so let me get out of this super full screen mode here, and I'll put up some stuff to just comment. But I feel like the second half, hopefully, that felt like sparks. I think it did. Okay, so real quickly, we talked about this, but if you were going to talk to other things, MongoDB, Redis, Postgres, files, even it's so ironic that the file IO operations in Python do not support async IO. Like, anyway, how do you do that, right? So real quickly, if you're going to do file IO, you can use AIO files, right? And so this is like a async with open. MongoDB, this is a really cool library called MicroMongo. And it does both synchronous and asynchronous MongoDB calls. It also has built-in mocking support and other things like that. It can also run on top of Motor, which is built on Tornado. And there's all sorts of like twisted rather. There's all sorts of interesting stuff happening. Postgres, you have Async PG. All right, so there's your Postgres angle. And Redis, there's a Async IO Redis, which is pretty cool. Very much like our Async IO.Q, you await getting an item, you wait putting an item, and so on. And that's it. So thank you so much. My name's Michael. You can follow me on Twitter at mkennedy. And I'll leave you with two really quick thoughts, and then I'll start taking some questions. So I have two courses that cover a lot of the stuff that you've seen today. If you're interested, please check them out. So I have an Async IO course that is like this, but actually like a 5 hours really in-depth coverage of these things. So if that's interesting to you, please check that out at talkpython.fm/async. And as Paul mentioned as well, I have a cool PyCharm course that covers so much about PyCharm. Check that out at talkpython.fm/PyCharm. And then that link there at the bottom is once again the link to get to the GitHub repo. And just in case you all want to look while we talk, there we go. I'll do a quick commit and push. And Paul, let's open up to questions.
All right. For you, the thing you just brought up with the async course, I strongly recommend it. Not just because it's good, but because learning it yourself is, it's a word that rhymes with hopeless. If I was to sit down right now and teach myself the state of the art of async in the world of Python, I could spend, 100 hours to save the money on your course. And I think your course works out to be, how many hours is it?
I think it's 5 hours. Unless you do the exercises and stuff yourself, then it adds more. All right, you can work on play around.
Yeah, and this is a course that I also recommend to people. Don't just breeze through it. Carve out some headspace, some quiet time, weekend, whatever, and work it. And make sure that on each step you know what you just did. Does that make sense?
Yeah. Thanks. I agree.
Question about Curio and Friends, these other Python libraries from esteemed people.
Yeah.
That are not Async IO. Because it kind of gets to a little bit of reaction in the Python community that I think the listeners should be informed about. Not everybody thinks that Python's Async IO in the standard library is correct. Want to comment?
Sure. I feel like Curio was created around the 3.4 timeframe, which means it's more event loop focused than it is async and await focused. I believe Trio is Trio definitely supports async and await, is much more interesting there. So I don't know as much about Curio, but Curio is very much a low-level library for building async things. Like if I want to create an application that talks on the network that does stuff deeply around async event loops, I could use Curio to build that. Like it's got like a TCP layer or something like that. That's pretty interesting. Curio, I believe, also has that. Sorry, Trio also has. Why did I have to end the same? Trio also has something similar to that, but Trio is more about coordination. So what we haven't seen is things like cancellation. So let's suppose I want to go download all that stuff off the website, but if any of them fail, I want to cancel the subsequent ones that I've scheduled but haven't happened yet, right? How do I do that? There's no mechanism at all. Well, I think there may be something in there, but it's not simple. It's not a simple API to do that. I can't put like a with block, and if there's an exception in one, it will automatically cancel the others. And Trio is all about that kind of organization and coordination. There's a really interesting example that Nathaniel gave at PyCon 2017 maybe, or 18, a recent one around Trio, and he basically re-implemented this this hard problem around timeouts and cancellation in Tornado, and it's like 1,500 lines of code in Python in Trio, or in like straight Async IO or Twisted code. No, it was in Twisted. So there's some really funky, hard algorithm that's like super complicated to hit all the edge cases, and it was like 20 lines of code in Trio because of the cancellation and coordination and like parent-child relationships of these tasks that you can create. So like, for example, you can create parent tasks that run 3 other tasks, and that parent task you can just await and it won't be done until its children are also done. And like that, those kind of like, sort of execution graphs are what that one's about.
And it's a reminder, because we got a bunch of questions about, boy, this doesn't look easy. I should do threading. No, I mean, the pain you can get yourself into with the kinds of things you just mentioned can be multiple orders of magnitude worse if you're doing thread code.
Yeah, I mean, we have like events and signaling and waiting and locking. There's like a lot of stuff that you get into. This is not super easy, but I mean, let me just give you one example here, right? We have that version and not that one. Yeah, that one. I just got to go up. All right, let me just cycle between those. All right, there's a lot of stuff happening here that's beautiful with not a lot of change in the API, right? And the error handling gets easier here as well. Like this will like return the return value of the multiprocessing call and all sorts of stuff. Like it gets a lot better.
And at the end of the day, the GIL is still there keeping you on the tracks.
Yeah, true.
Okay. Can we use several different kinds of event loops in one program? I come from Pyramid, and I've seen talk about using Async IO in Pyramid alongside an existing like G event kind of whiskey.
Yes,
server.
but I think you have to coordinate the mix and matching.
You have to
of it.
Yeah, right. There's no like free lunch on that unless someone has gotten your free lunch for you.
Yeah, like for example, if you look at this thing here in this unsync thing, like it actually creates its own event loop and it runs it on a background thread. So the unsync is interesting in that it doesn't even do your async work on your thread. Your thread is still available to go do other things, which could even be a regular, event loop or something, I suppose. But yeah, you can, but it's kind of, you're getting down to like coordination and whatnot.
Yeah. So on that topic, we have a point, not a question. Using the unsync decorator is not necessary if we know that the method is not async. So does unsync simply help developers so that they don't need to look at the type of functions?
It's unnecessary, but it's a different behavior. Let me show you. I have to change my weighting code, but here's the thing. Notice this compute sum, computing, and then let me just print compute done. Look at this, computing, starting, compute done. That's not the same as calling compute without unsync, right? What this is doing is this is saying this is CPU bound, so I run it on another thread. Sorry, I run on multiprocessing. This one, which I didn't change, but here, this one is actually running download some more on another thread. So this would be the equivalent of saying, create me a thread, start the thread.join, instead of just wrapping it with this decorator. right? So just to be clear, like what's happening, it's not that I'm calling it and it's just running. I'm doing threaded work and receiving the return value. And it also captures the exception on that thread and brings it back in the way that we talked about before. So it's doing a whole bunch for you, even on this basic one.
All right, last one. Is your Talk Python podcast on Spotify?
No, it's not on Spotify. That's
You've
a
got
good
like
question.
100 choices for how do you
I know. Let I know it's here. You can let Ben and crew talk about why the problem with Spotify and the podcasts and why they aren't, and I agree with much of their reasons. Basically, Spotify is trying to create a walled paywall, a walled garden, a paywall around popular podcasts, and I don't think that's a super good thing for the industry. So I don't want to feed the beast, and so I'm not on Spotify.
Good for you.
But it's on many things, right? Like Google Play, iTunes, and everything derived from there. For example, Overcast and Pocket Casts and things like that.
I warn everyone, once you go and look at all of the episodes, you might as well kiss goodbye to 30 hours of your life. There are some things in there. I was traveling recently and listened to your talk with Peter from Anaconda.
Thanks.
And,
that was a good one.
Boy, that was the provocative one.
Yeah, he's got some really wild and insightful ideas.
Oh, yeah, on some urgent issues.
Yep.
All right, let's switch back to my screen. Thanks, Michael, for taking the time to talk with us about Python and Async.
You're welcome, and thank you everyone for coming and sticking around.
Hey, Michael, should people come to see us at PyCon?
You know what? We're going to have a pretty epic booth at PyCon. Yeah, so definitely they should come see us. I don't think we've really announced this before, have we? So why don't you do it?
This is a webinar special, isn't
it? You all get the scoop.
Yep. All right. Pay attention in the next couple of months or a couple of weeks. We're going to announce some information about the PyCharm booth at Microsoft. It's going to be really fun. If any of you have any questions later, I believe we've answered all the questions now, but if there are any others or you think of anything later, don't hesitate to reach out to us by email or social media. If you'd like more information on PyCharm, please go to our website at jetbrains.com/PyCharm. We'd love your feedback on this webinar. Narrator, everyone loved the webinar. So please feel free to contact us on Twitter or in the after webinar survey. Fill in the survey. We look at it and it helps us decide how to get better as well as other webinars that we should do. The recording will be made available on our YouTube channel soon. If you haven't already, please check out the PyCharm blog. Please check it out. We're putting a lot of work into it. On our blog, you can find up-to-date news about PyCharm, about releases and events, in addition to educational resources. Just a pro tip, you might want to watch out for the next blog posts for the next EAP coming out. So, for example, the recording of this webinar will be published on the blog in a few days. We'll also provide some additional links and information from the presentation on the blog. That's all from us today. Thank you very much, Michael. Thank you to all of you for joining us and hope you have a nice day.
Thanks. Bye.